Hey everybody, welcome. We're going to be getting started here in just a couple of moments. Say hello in the chat while you wait. If you're planning on taking the P exam in 2025, we did just start the winter live class semester. We're only on week 2 out of 11. It's a great time to join in, jump on in the semester, and learn everything you need to pass the exam. All right, everybody, welcome back. This is week 2 of our qualitative practice exam book launch series. It's promoting our new book, Mastering the PE Exam, 100 Qualitative Practice Problems for the Electrical Power PE Exam. It's just about 260 pages, 100 questions. It follows along with our live class semester. So you've got anywhere from about 10 to 13 problems each for each of the main subjects on the PE exam. Last week was week 1, so we can cross off January 9th, 2025. Today is week 2, January 16th, 2025. I'll be running this for 2 more weeks after this for a total of 4 weeks. So we'll be meeting next Thursday, January 23rd, and the Thursday after that, January 30th, same time, noon Eastern time. So during this book launch webinar series, if you're interested in an early copy of the practice exam, it's currently on sale on Amazon.com for $20. This is the lowest price. Amazon will let me price this book. I receive exactly $0 in royalty at this price. I'll probably keep it at the low book launch price for probably a few more weeks. Goal is just to get it in as many hands as possible for anyone that's studying for the PE exam. Easiest way to find this book on Amazon.com is just search for my name, Zach Stone, include the PE at the end. You'll see my author profile. You'll see all of our books available. Good. Y'all just said mine arrived this week. Great. Yeah, Eric, absolute bargain. Valentina, thank you. Said I just purchased the book today. Wonderful. Book's been about a year and a half to 2 years in the making. And what's the purpose of this book, right? It's not your typical practice exam. It's not 80 questions like the real PE exam. And I've got all of the solutions pretty much one chapter at a time. So after circuit analysis, you've got the circuit analysis solutions. After the transformer questions, you've got the transformer solutions, et cetera, et cetera. So the goal is really to work this in your studies over the course of your study period leading up to the PE exam. If you've been paying attention, if you've been hanging out on any online forums, on LinkedIn, on Reddit, on our online community, anything like that, you've probably noticed that everyone that's been taking the PE exam lately over the past couple of years, they've all said the same thing. The PE exam is becoming more and more qualitative, meaning you got to rely less on this to pass and more on this. So a lot of these are theoretical concepts, theory concepts. If I change one variable, what happens to the others? If I increase it, do the others increase? Do they decrease it? Is it a linear relationship, non-linear relationship, etc.? So a lot of this stuff, they're testing you on things that you should run into during your career as an engineer. It's testing quite a bit on experience, but depending on what particular industry you're in, whether it's building construction, whether you come from the industrial world like I did, maybe you're doing data centers, even telecom, transmission lines, protection controls. There's a lot of the things they're going to test on that are just, outside of your lane, outside of your specific career path. So the good news is I'm going to show you how to solve just about all these qualitative questions. And anytime we can break it down using the fundamentals to approach these in an intuitive way, I'll always do that. Why? That just means less to memorize, right? So yeah, really important passing the PE exam. You should be focusing more and more on qualitative questions. I would say as much as quantitative questions, right? Quantitative questions being when we plug numbers in our calculator and we're trying to select the answer that matches what we get on the calculator. So I'd say paper and pencil, right? Years past, the PE exam definitely seemed to be more quantitative, and now it's probably 50-50. So qualitative questions, theory questions, application-based questions, like what's the right motor for this application, variable relationships, they're all just as important as being able to work with complex numbers, square root of 3 relationships, circuit analysis relationships, power fundamentals. So they're all equally important. Okay, so last week we went through problems 1 to 4. So we're going to pick up where we left off on page number 12, starting with problem number 5. Any questions before we get started? Any questions before we get started? Let's see. Crystal said, are these the same exercises that are at the end of each class section? So Crystal, yeah, if you're currently enrolled, you've got access to the early release version in PDF format of this book. You've got the individual chapters at the end of every class homework assignment. So the early release version, I think it's about 60 or 70% published. And then in about a month and a half, once the digital version of this book is published, we're going to be including it with both of our paid enrollment plans at no cost. So if you're already enrolled, you will have access to the full PDF of this book probably in about a month, give or take. All right, are we ready to get started? So problem number 5, power factor correction and power flow. I'm going to go ahead and read the problem, and then I'm going to read the answer choices and give me the answer that you think it is in the chat. So 5 says, which of the following are suitable applications for capacitor banks and electric power systems? A, power factor correction. B, voltage support. C, series transmission line compensation. Or D, all the above. What do we think? See a couple of A's right off the bat. Yeah, anytime when I see capacitors, their number one application in power systems is for power factor correction, right? Power factor correction is one of the subjects on the PE exam. Good, I'm seeing a lot of D's. I'm seeing a lot of all that applies. All right, what do we think? First of all, everyone knows what power factor correction is, right? Most common application of capacitors. We use them to supply reactive power to improve the power factor of the system. Most common use case of that is induction motors, heavy lagging loads. Instead of supplying the reactive power that the induction motors need from the power supply from the utility, we can install capacitors that act like a reactive power supply. And the whole point is to save money, right? If we're a large facility, large customer, have a lot of motors, we might have a pretty bad power factor, and the utility company might charge us a power factor penalty fee that in the long run is more expensive than say investing, in large capacitor banks. Typically maybe there's a 3 to 5 payoff period there. So that's power factor correction. What about voltage support? Anyone know what voltage support is? Hey, Jerry, you're on host and panelists. Check those chat settings. Switch over to everyone. So power factor correction is one of the applications. Any guesses on voltage support? So in addition to reactive power, what do capacitor banks supply? They are capacitive loads, and they supply capacitive current. Now, most systems are going to be lagging, right? The only time we really have leading loads are if we have capacitors, which we're usually using to correct the system, or if we have overexcited synchronous motors, which are pretty rare, right? Even in a big facility that does have those, you don't typically have a lot of them. They're very specific types of motors. So voltage support is also a suitable application for capacitor banks. And what that is when the capacitor is supplying reactive current while it supplies reactive power, that reactive current cancels out a little bit of the inductive current drawn by the inductive loads. And what that does, it'll actually decrease the current a little bit. Think about it. Lagging current lags the voltage, leading current leads the voltage. So the two of them cancel out. It's like having a positive number summed up with a negative number. So when the capacitive current cancels out some of the lagging current, your overall current decreases, which also decreases some of your voltage drop as the current flows through the conductor. As we decrease the voltage drop, what happens? Well, decreasing the voltage drop means I'm actually increasing the voltage available at the load, right at the load. That's voltage support, another application for capacitor banks. How about C? What is series transmission line compensation? What is series transmission line compensation? So typically capacitor banks, how do we install them most of the time? Do we install them in series or do we install them in parallel, or typically we call that shunted? Yeah, we usually shunt them, said Caleb. Well, series compensation is a very specific application of capacitors where we actually install them in series with our transmission line conductors. If you're in our online class for the PE exam, class 11 end of life class test has an excellent quantitative problem on series transmission line compensation using capacitors. I think it's problem 14 on the end of lab class test. But when we install these special capacitors in series with our transmission line conductors, what happens? Our conductors, whether it's a small wire in your wall at your house or a big distribution feeder or a big transmission line conductor, are conductors inherently capacitive or are conductors inherently inductive? And if you're not sure, here's a hint. Think of the National Electrical Code, Chapter 9, Table 9, the table that we use to look up the effective impedance of conductors when we're solving for voltage drop. Are they inductive or are they capacitive? Conductors, when they carry current, they're inductive. Yeah, they're inductive. Good job, Daniel. So when we install a series capacitor, which is instead of being an inductive reactance like the conductor, it's a capacitive reactance. It's a negative J of X. What does that do to the conductor when we view the whole thing as a whole piece? What does it do? Instead of if I were to draw like an impedance triangle pointing up with an inductive reactance, a positive imaginary component of the impedance for the conductor, the capacitive reactance would be pointing down. And that helps to decrease the overall impedance of our transmission line. So the negative capacitive reactance, again, we're canceling out some of the positive inductive capacitive reactance of the transmission line. What happens when I decrease the overall impedance as current flows through it? Now we're back to talking about decreasing voltage drop again. When we decrease voltage drop, what happens? We've got more voltage available at our load. So series transmission line compensation, it's also an application for capacitor banks, which makes the answer to this problem D, all of the above. All right, on the next page, I've got a summary. This is the solution that's provided in the book. Who here has used or worked with capacitor banks in their day-to-day? Anyone here worked with capacitor banks either from a maintenance standpoint, from a design standpoint, anything like that? Sarah, great. Anybody else? Quite a few. Good. Daniel, Joshua, Michael. How about anyone use capacitors for voltage regulation? Did anyone use them for voltage regulation? Daniel said, yep. Eric said me. On the grid operator side, said Caleb. What about anyone here ever work with or work around capacitors for series transmission line compensation? Keyword there is series, right? It's the only time we really install capacitors in series. Otherwise, we typically install them shunted when we're typically using them for the most often use cases, power factor correction. Daniel said, yep, me as well. Good. All right, any questions on number 5 before we move forward? Any questions on number 5? Voltage support also, if you look at the NCEES examining specifications, voltage support is also a topic in addition to power factor correction. Let's see, Ryan said, cool. Ryan said, I'm currently using them for a snubber on a transformer to mitigate transients. So yeah, in that case, what, Ryan, using them as a really large filter, right? Big filter to snub out any transients. Great. All right, that's it for number 5. Let's take a look at number 6. So again, I'm going to read the question out loud, and I'll read the answer choices. Give me the answer you think it is in the chat. What happens when the load connected to a transmission line at the receiving end is equal to the transmission line's surge impedance loading? Good vocabulary word there, surge impedance loading. SIL for short. Do we think it's A, the transmission line will deliver maximum current to the receiving end? B, the transmission line will deliver maximum power to the receiving end? Do we think it's C, all the reactive power absorbed by the transmission line will be supplied by the capacitance? Or do we think it's D, all the reactive power absorbed by the transmission line will be supplied by the sending side? A, B, C, or D? What do we think? This must be a tough one. Any guesses? Fred said B. Any other guesses? Maybe we're just not sure. So I'm seeing mostly B's, transmission line will deliver maximum power. I see D from Jerry, reactive power absorbed by the transmission line will be supplied by the sending side. All right, let's take a look. That lets me know this is a good problem. So the answer is actually C. All of the reactive power absorbed by the transmission line is going to be supplied by the transmission line capacitance. Another way to think about this is the transmission line is supplying exactly 100% of the reactive power that it's going to consume. It's like feeding itself reactive power. So here's the easiest way to think about this. I'm going to zoom all the way in here so it can be as clear as possible. So on your screen, you've got a medium transmission line equivalent circuit. This is in section 5162 of the NCEES reference handbook. Transmission line, we've got two sides, right? We've got a sending side on the left, receiving side on the right. This is where we connect our load. This is what we think of as our power supply on the left. So your transmission line, right, depending on the conductor that you're using, you've got a resistance and an inductive reactance plus JX of L. What kind of power does a inductive reactance absorb? What kind of power? What's the name of that power and what are the units? It's not what? It's not watts, right? Resistance consumes real power watts. VARs. Great job, Yelda. Yeah. This positive JX of L, it's an inductor. It's an inductive reactance. This right here is going to consume reactive power Q in the unit of volt amps reactive. That reactive power has to come from somewhere. If the load on the receiving end of our transmission line, if this is equal to that vocabulary word, the surge impedance loading, so if this is equal to our surge impedance loading, then all of the reactive power absorbed by the reactance of the transmission line. And remember, this is just modeling the what? That's just modeling the conductors on the transmission line. This R, this J, X of L, even the shunt admittance, that's the properties of the actual conductors themselves. When you drive along the road and you see the big transmission lines, maybe down the highway, this just models the big transmission line conductors. So all the reactive power absorbed right here, 100% of it, the exact amount, gets supplied by the shunt admittance. Now we use admittance to model the capacitance, right? Admittance is just the inverse of impedance. But who here has worked a transmission line problem when you're calculating the line capacitance using the natural log, DEQ divided by GMR sub C? You've got a couple of big coefficients there. That's what this variable is right here, right? What kind of symbol is this? This is a capacitor. Capacitors supply reactive power. So when the transmission line load, when it equals exactly this value known as the surge impedance loading, then it's perfectly balanced in terms of reactive power. It doesn't need to consume any reactive power from outside the transmission line, or it's not producing an excess amount of reactive power that it ends up sending some reactive power to the receiving end. It's perfectly balanced from a reactive power point of view. Does that make sense? Kind of like how we talked about in the previous question, capacitor banks supply reactive power. Well, think of these as capacitors. Now, in real life, am I connecting two capacitors in parallel at the start sending and the end receiving side of my transmission line? Am I actually putting a big capacitor there? Or is this just what? This is just a model. The two capacitor symbols on your screen, that represents the naturally occurring capacitive characteristics of our transmission line, of the conductors between themselves and a little bit between the conductor and ground, where the conductors almost behave like two plates on a capacitor. All right, so looking at a few other good things to note in the solution, right? This pretty much just sums up what we talked about. When the transmission line is terminated in the surge impedance loading, it's going to be balanced in terms of its reactive power. It's supplying all of the reactive power it needs and no more. Very similar concept if you've been working through synchronous machines. It's a very similar concept as a unity power synchronous machine that has ideal excitation. It's neither exporting VARs or importing VARs. It's got a net reactive power of 0, right? It's providing its own reactive power, no more, no less. All right, so when our load is equal to the surge impedance loading, we've got net 0 reactive power. What happens when the load is either less than or greater than our surge impedance loading? So when the load is less than the surge impedance loading value, then the reactive power supplied by our shunt admittance, which is the capacitors in our circuit model, it's going to be more than, greater than the amount absorbed by the inductance. What happens if this plus this is greater than this? Then what? We've got an excess amount of reactive power. Where does that excess reactive power go if our load is smaller than the surge impedance loading? It's got to go somewhere, right? Excess reactive power. In that case, the excess reactive power, it's going to go where? It's going to go to the receiving end. The amount of reactive power absorbed by the inductive reactance of those transmission line capacitors, it's less than the total amount of reactive power being supplied by the shunt admittance. So now we've got some excess reactive power, Q in units of VARs, being sent to the receiving side. Great vocabulary word. Anytime, all the solutions, this is one problem. There's about 10 different things that this solution could be the answer. It's about 10 different problems we're working here. Another great vocabulary word you should be familiar with for the P exam, it's known as the Ferranti effect. When there's excess reactive power being sent to the receiving side, the voltage on the receiving side is going to be greater than the voltage on the sending side. VR will be greater than VS. This voltage across our load will be greater than the voltage at the beginning of the transmission line. It's not always a desirable effect. A lot of times, if we're not careful, it can lead to over voltage conditions. Anytime we're dealing with over voltage conditions, the biggest issue we're looking at is damaging insulation. Insulation is typically rated in volts. You can blow that insulation voltage rating. So Ferranti effect, undesirable. What's the opposite? What happens when instead the load on our transmission line, what if it's greater than our surge impedance loading? What if it's greater than? Now, guess what? The amount of reactive power absorbed by that series inductive reactance, it's greater than the amount of reactive power being supplied by our shunt admittance. Instead of having an excess of reactive power, now what? Well, this series inductive reactance, is it only going to consume what these two capacitors deliver to it in terms of reactive power? Or what? Is it going to take reactive power from somewhere else? What's it going to do? It's going to take reactive power from somewhere else. This series inductor right here, depending on how big that reactance is, it has a set amount of reactive power that it's going to consume when current flows through it. So if all of that reactive power, if those needs are not met by the reactive power being supplied from here and here, then instead of exporting reactive power to the receiving side, it's going to draw reactive power from the sending side. In other words, There's not enough reactive power to completely satisfy it. We don't have quite enough. So instead, it's going to pull some from the sending side. Again, these are concepts similar to excitation when we're dealing with synchronous machines and overexcitation and underexcitation. Are we exporting VARs? Are we importing VARs? What happens then? Now, instead of the receiving side being greater than the sending side, now the receiving voltage is going to be less than the sending voltage. Interesting. Now, a couple of things we want to point out. In real life, do we always get a perfect match? Do we get that perfect surge impedance loading on a transmission line? Not really, right? In real life, we build a transmission line, we try to future-proof it as much as our dollars will allow, as much money we have in the project. We're going to try to future-proof this transmission line because it's going to be cheaper to build it with extra capacity than it is to go back and upsize it, right? So in real life, rarely ever do we get a perfect match on the load to equal the surge impedance loading. So your surge impedance loading, this does not represent maximum loading. And in real world conditions, a lot of times it's going to be greater than the surge impedance loading, right? We're adding more and more and more power. More homes are being built. More factories are being built, right? Typically, the demand of our electric grid is outpacing what we currently had built 10, 20 years ago. Make sense? Now, in the reference handbook, we've got the formula for surge impedance loading. And the reference handbook does this quite a bit. They'll give you the formula for something, but it's up to you to know what it is in order to use it, for example, to answer this kind of question. So I'm going to zoom back all the way in. I'm going to show you on the next page. Here's the formula for surge impedance loading, SIL, in the reference handbook. It's in section 516, transmission line models. It's really interesting to point out, what are my units for surge impedance loading? What are my units? This is in units of watts. So we can calculate the surge impedance loading all day. If I come across a quantitative question, if it says calculate the surge impedance loading, I go in the reference handbook, I see my formula, I punch in the numbers, and I select the answer. But the formula by itself, it's not enough to answer that qualitative question. However, we can solve for the surge impedance loading using the S equals V squared over Z formula, where we take the square of the transmission line voltage and we divide it by a special impedance known as the line surge impedance. This formula is also in the reference handbook in the same section. The surge impedance is equal to the square root of the ratio of our series transmission line impedance divided by our total shunt admittance. If I go back to our transmission line model, if I were going to calculate ZS, the surge impedance, as the square root of the ratio of Z over Y, here's our total Z. This is our complex impedance right here. Complex Z equals the resistance plus J times the reactance of that transmission line conductor. Then Y, our shunt admittance, is the total shunt admittance right here. When we use the medium transmission line model, what we call the pi model, we take this value, the shunt admittance, we divide it in half, we stick half of it on the sending side, we stick the other half on the receiving side. We distribute it half on the front, half on the back. But in the formula, we're using the total amount. If we can calculate the surge impedance, then we can calculate the surge impedance loading. Quick question in the chat. Does this formula look familiar? ZS equals the square root of Z over Y. Does that look familiar? Anyone seen that before? Sarah says yes. Yeah. Where have you seen that before? That same value also goes by another name. Yeah, great job, Eric. Eric said the characteristic impedance. Typically, we use ZO. Same value. Characteristic impedance, also does what? It eliminates something called reflective sending waves on the transmission line. Another good qualitative topic. Same value. When we're talking about reflected sending waves, we describe this value as the characteristic impedance, ZO. When we're talking about reactive power consumed by the transmission line, and if it's being supplied by the transmission line, or if the transmission line's not supplying enough and some of it's being sent from the sending side, or if the transmission line is supplying too much and we have an excess amount being supplied to the receiving side, then we call this the surge impedance. But it's the same value, same formula. All right, any questions? This is a really in-depth qualitative question. I can think just off the top of my head, easily 10 to 15 qualitative questions that you could expect to see on the P exam based on the information we just talked about right now. Any questions? This is I would categorize this one as a harder one too. Typically, characteristic impedance is what you see come up more often, but being aware that it's also the surge impedance and that we can use the surge impedance to calculate the surge impedance loading, and then knowing what effect the load on the transmission line has when we compare it in size to, is it bigger than our surge impedance loading? Is it equal to our surge impedance loading, or is it smaller than our surge impedance loading? Good question. Valentina said, how many transmission line questions are typically on the exam? I don't have the exam specifications pulled up in front of me, but it'll definitely show you the range in the exam specifications. Definitely show you the range. All right. Any other questions? Okay, that's question number 7. Excuse me, that's question number 6 on surge impedance loading. Let's take a look at number 7. 7's pretty quick. This is for our class number 8 per unit fault current analysis and symmetrical components. So number 7, what's the main purpose of the per unit system in electrical engineering? Is it A, to simplify calculations and comparisons by normalizing values? Is it B, it eliminates the need for transformers and power systems? Is it C, it allows for the direct use of real world units without conversion? Or is it D, none of the above? What do we think? All right, I'm seeing just about all A's in the chat, flying in the chat there. Great job. To simplify calculations and comparisons by normalizing values. Anyone else? Or rather, did anyone else select anything other than A? Nah, good job. Answer is A. So yeah, the whole point of the per unit system is to simplify our calculations and especially our comparisons. When we normalize everything to the same base, I can look at the per unit current and know right away. If my per unit current is equal to 1, it's the same rated values compared to my chosen base values. If it's bigger than 1, if a per unit of 1 current represents the maximum rated current of that transmission line or system, and I've got a per unit current of a little bit more than 1, I know my system is overloaded. Or if it's less than 1, I know, hey, I still got some room. These conductors can still handle more current. When we're dealing, especially with big distribution systems, transmission systems, we have a lot of voltage transformers, right? From stepping up at the generating side, in the United States, the most common generated voltage is 13.8 kV. And typically we're going to step that up depending on the size of the generator. If it's a distribution generator or transmission generator, we're going to step that voltage up to either transmission voltage or distribution voltage. We're going to send that voltage. And then at the point of utilization where the customers are, we're going to step it down. And depending on the customer, we might step it down several times. If it's just a residential customer, like right here in my house, then it's just being stepped down once. It's being stepped down by the transformer on the pole outside my house to split phase 120, 240. But if it's a big customer, a big commercial fabricator, big industrial plant, maybe it's a mining location, you could have everything from, 13.8 kV, 2400, 4160, all the way down to 480, and then all the way down to 120. So when we're looking at single line diagrams with all these transformers, the per unit system, it doesn't eliminate the need for transformers and power systems, right? We still need them in real life, but it eliminates the changing of voltage and current with respect to the different voltage zones when we're looking at the model of our system, either on paper or on maybe a, power flow study software. So it just makes it easy. I can compare apples to apples right away, and I can compare it to our chosen base values of the system instead of thinking like, okay, well, I've got 1200 amps here, but here's a transformer. And now we stepped up and I've got, maybe 150 amps, but how does that relate to the 1200 amps? Maybe you have to work through this transformer and see what that value is. Is that backwards or forwards? So the per unit system, it's, you're normalizing everything to essentially 100% or one per unit. So right away, I know, is it too much or is it undersized? So I still have some room. Does that make sense? So B is false. A is the correct answer, right? We said it doesn't eliminate the actual need for transformers. I still need transformers out there to get my utilization voltage, but it simplifies the model, so to speak. What about C? C was also false. Allows for direct use of real world units without conversion. Right, that's just the phony answer. All right. Any questions on the per unit system? Yeah, Mark said, I hope this question will be on the exam. Yeah, it's not too bad. A lot of people, though, panic when they see the per unit system. A lot of people don't have a really strong comfort with the per unit system. So this question, even though it's pretty straightforward on the surface level, can still solve a little bit of panic. Did anyone here feel a little bit uncomfortable when they realized this was a per unit question when I was reading it out loud? Did anyone have that kind of visceral gut feel? Oh God, I hate per unit. Yeah. All right, that's seven. Number eight. Number eight's a fun one. This is protection coordination. The problem shows one TCC curve, but in the solutions, we're going to look at all of the TC curves mentioned in the possible answer choices. So again, this is one problem on paper, but really we're going to be working through about four different possible problems, even more. All right, ready? Who can tell me number eight? What type of protection device is most likely represented by the time current characteristic curve shown below? Here's our TCC curve. We've got a log scale on the horizontal current axis. We've got a log scale on the vertical time axis. Is this A, a thermomagnetic circuit breaker? Is this B, electronic trip circuit breaker? C, is this a fuse? Or D, is this some type of ANSI combination 50-51 protection relay? What do you think? All right, I'm seeing A's in the chat. I'm seeing some C's. I'm seeing some B's. Okay, great. How about out of these four, is there one that we can eliminate pretty easily? Maybe we're not a protection engineer. Maybe we're not really familiar with all the different curve types of the various different types of overcurrent protection devices. But is there one curve that's really easy to spot for what it is? Which one can we eliminate right away? Yeah, eliminate the fuse, says Daniel. Charles said definitely not a fuse. Correct. What does a fuse typically look like? And I've got it coming up. But a fuse is kind of typically just like this, more or less, depending on if it's current limiting or not, but we're definitely not going to have this instantaneous trip section, right? It's really just a silver curved area. So it's not a fuse. So I would eliminate that one right off the bat. All right, ready for the answer? The answer is A. This is a thermal magnetic circuit breaker. So how do we know? How is this a thermal magnetic circuit breaker? Thermal mag breakers really only have two distinct trip functions, or we can say that as two distinct time current curve characteristic regions, right? Who here works on thermal mag breakers? What's one of the most common applications? What's one of those common applications of we typically just call a thermal mag? Yeah, in your house? Sure, Charles. Yeah, great answer. Not what I was expecting, but absolutely, yeah, correct. I've got a square D panel in my house. It's a QO load center. Those are thermal mags. Panel boards, branch circuit. So for me, the most common ones I've worked around, motors, MCPs, motor circuit protectors, breakers built specifically for motors. In fact, I've got a three-phase one, Cutler hammer one right off my right shoulder. I don't know if you can see it. Those are what? Those are typically always going to be a thermal mag breaker. Thermal mag stands for thermal, which means what? What does thermal mean? Thermal means heat. Mag means magnetic. So thermal mag breakers have two main regions. What region is this down here? That big fat horizontal rectangle that sits right on our horizontal axis, or sometimes if you can adjust it, there might be a little gap here, but for the most part, it's going to be pretty close. That's always our what? Yeah, that's always our instantaneous trip region. Instantaneous trip is for what? Instantaneous trip is for high fault current. This is for protecting against short circuits. We want it to trip as soon as possible, as minimal delay as possible, because we've got a really high fault current. So the longer it persists, the more damage occurs. When I say long, I'm talking about in terms of cycles, which are a blink of an eye in terms of, a human sense of time. So the instantaneous trip, the magnetic region, we want it to pop right away. On a thermal mag breaker, why is this called magnetic? Why do we refer to this region or this trip function as magnetic? Does anyone know how they work? Ever take them apart? Really neat devices. The way they're built, you usually have I do my best to draw, but you've got like a hook inside of it, right? Like the metal that the current travels through in the breaker curves. And when I have a really high fault current, I also have what? Anyone familiar with Maxwell's equations? Not in the P exam, but at least that relationship. More current equals more flux or a bigger magnetic field, right? They're proportional. More current, more amps, more magnetic field. So as the current flows through the hook shape, the curve, and the breaker, when the current is really big, the magnetic field around it is really big, and it ends up creating a magnetic field strength so strong that it opens the breaker contacts. So at all times, when that breaker is closed under normal conditions, non-overcurrent conditions, you've got a little bit, that curve in the shape, you've got a little bit of, and here we can even, maybe here's a contact right here. This is an oversimplification of this, by the way, but you've got a shape built into the metal that makes the the electrical contacts want to open from the magnetic field created by the current traveling through it. They build these breakers with very specific ratings such that for this one, look, this one, it's going to trip as low as 10 amps. So it's going to, at 10 amps, that magnetic field is just strong enough to open the contacts, trip the breaker, de-energize the circuit. That's for high fault current. That's the magnetic trip function of a thermal magnetic breaker. All right, what about the thermal trip function or the thermal region on the TCC curve? What is this designed to protect? Not high fault current, not short circuit current. That's our instantaneous magnetic region. Overload, said Mitch. Yeah, overload. Overload. Instantaneous trips as soon as possible. Overload, you've got a little bit of what built into it? You got a little bit of time delay, don't you? A little bit of time delay. Look, if I've got 1 amp of current, by the way, this could be, an MPU scale or times 100 times 1,000. So this one could be 100, this 10 could be 1,000. So anyways, if I've got 1 amp going up here, it's not gonna trip until right about here. Got a lot of time delay built in, almost 1,000 seconds. So the overload region, the thermal region, it's designed to protect against gradual increases in current. Again, I worked around a lot of motors. So I think about motors in dusty environments. The fan attached to the rotor isn't as efficient anymore and cooling down the motor windings. What happens? The motor starts to draw more and more current as the motor gets hot, right? Hot temperature actually increases the load on electrical machines and drives. So the hotter physically that this thing gets, it's like if I covered up a motor with a thick, heavy blanket, right? It's not going to have efficient cooling. That actually makes the current it draws increase. And it's like a runaway effect. The hotter thermally it gets, the more current it draws. So we want to protect it from those conditions by opening a breaker. Is it going to have immediate damage to that motor or that device as it's overloading? No, not really. And some overloads are going to clear up on their own. Maybe we've got just a heavy loading condition, right? But we want to protect it from prolonged overloads, which are going to damage the equipment. How does this work inside a thermal mag breaker? Thermal mag breakers, they're really mechanical devices. They operate on mechanical principles, like this shape for the instantaneous magnetic region that the magnetic field is slowly trying to pull the contacts apart. Well, the thermal overload, you typically have pieces of metal or springs that after a while, as they heat up, again, they're going to open the contacts. And those physical characteristics of the motors are built specifically at different ratings. So you can have different thermal ratings in your thermal magnetic breaker depending on the application. Who here has never worked with a thermal mag breaker? You're just not familiar with it, or who here is learning this for the first time? You can spend a lifetime on in protection on time current characteristics. Yeah, quite a few. The good news is, um, this seems really in depth, and not that it isn't, but once you start to learn a little bit about just one type of device's trip functions and trip curves, you can start to apply that same thinking to other devices. So this was the TCC curve in the problem, and it's for a thermal mag breaker. We talked about the long trip or the thermal trip or the overload region, right? We talked about the instantaneous trip function. Good point to point out is this is the most common of anyone here know what's a molded case circuit breaker, MCCB? What's a molded case circuit breaker? What does molded case mean? That's when you have a breaker made out of plastic, molded plastic. The case of the breaker is molded in plastic. The most common types of breakers are thermal mag breakers. Like, let's see, who said earlier in your house? Like Charles said, yeah. If you go look in your house panel, if it's a somewhat modern house, all of those plasticky little breakers, those are molded case circuit breakers. Thermal mags are the most common type of molded case circuit breakers. All right, how about let's look at the other TCC curves of the other possible answer choices, right? Anytime we get a question when we're studying, we don't want to know just why is the one particular answer the correct answer, but it's also really helpful to investigate, okay, if this is correct, why are the three other possible answer choices not correct? Because what if they ask me to identify a fuse? What if they ask me to identify a relay curve, et cetera, et cetera? So let's look at the other trip functions. All right, next one, electronic trip circuit breaker. First of all, what's the dead giveaway that this is not a thermal magnetic circuit breaker? What's the unique characteristic of a thermal magnetic circuit breaker? How many types of trip functions does it have? Which is the same number of trip region on the time current characteristic curve that represents those trip functions. Yeah, thermal mag only has two. We have instantaneous trip, no time delay, and we have long time thermal trip. How many different trip regions do I have here? Of quite a few, don't I? I still have, look, here's our instantaneous trip region. So we still have an instantaneous trip. Here's another trip region. This would be probably our short time delay trip region. And look at this. This is like a long time trip region. So how many trip regions? See if I can draw a rectangle. How many trip regions does this device have? We got at least three, right? Way more than two. So electronic chip circuit breakers, all the times, these are the ones that are much more adjustable. And look, yeah, it has at least, a lot of times they can have more, but at least three tripping functions. So the ones we just drew was the instantaneous on the bottom, right? And the short time, and then the long time. Long time is always your overload, but maybe I want more flexibility in my protection settings so that, hey, I don't just want to trip all the way out here, right? From here all the way to about what? 200 seconds, right? Maybe I want a little bit of tripping here in this region. I want to be a little more selective. Who can tell me why are they called electronic trip circuit breakers? Anyone work around these? And we'll compare them to thermal mag breakers. Really, they're operating with mechanical principles according to physics. The shape of it allows the magnetic field to try to pull apart the contacts on the instantaneous region. And then the metallic pieces inside, we use special pieces of metal that melt and typically we let a spring open the contacts for the thermal, right? These are mechanical properties. These are physical properties. How does an electronic trip circuit breaker work? Keyword is this word right here, electronic. Let's see, battery operated for Mike. Hey, Mike, you're on hosting panel. Let's see if you can switch over to everyone on those chat settings. They're smart, said Valentina. Ah, Brooklyn. Yes. Brooklyn said because they trip electronically. Yeah. Electronic trip circuit breakers have built-in electronic sensors. So we use electronic sensing devices to trigger the tripping of these breakers. These are not mechanically tripping breakers like thermal mag breakers. These are electronic trip circuit breaker. We've got electronic sensors sensing the current. So why would we not always use electronic trip circuit breakers? Why not just always use them over a thermal mag if they're more adjustable, more regions? Well, answer to most of those questions are always what? Yeah, more money. More money. And oftentimes you don't need them, right? This whole house, I'm protected all by 120 volt molded case thermal mag circuit breakers in my panel for all of my lighting and receptacle loads. And then my bigger loads, I've got two pole thermal mag breakers that are molded case circuit breakers, for my range, my dryer, that kind of stuff. But I don't need more sensitive tripping. I'm only tripping on the absolute worst short circuit, or I'm tripping on prolonged overloads. I don't need this additional trip region. It's just not really needed. I don't need to spend that extra money. Let's see. Brooklyn said, yeah, usually the thermal mag just needs to protect small motors or small loads. Don't need complex protection. Exactly. What are these typically used for? When do I want more flexibility? A lot of times you got big feeder breakers, right? So thermal mags, a lot of times we use them for branch circuit protection, the last overcurrent device in that circuit. What about if I've got a big feeder breaker that feeds a panel and that panel feeds 40 some loads? Well, maybe have that one feeder breaker is protecting all of those loads connected to the panel. So I want to be able to have more customization. I want to be able to really fine tune the protection of that entire panel fed from the feeder breaker. So feeder breakers a lot. You're going to have more sensitive, more complicated, more sophisticated protection. All right, see, here's our fuse. Remember we talked about we could eliminate that fuse choice. Everyone see the shape of the fuse? Dead giveaway. The fuse is the easiest thing to recognize. Our fuse is adjustable. And I would say basic fuses because some fuses you can add or take out links, right? But your common off-the-shelf fuse, they're not adjustable. What you see is what you get. What you see is what you get, not adjustable. And it's, yeah, look how it's very close to a vertical line. Got a little bit of a curve there, but it's more or less a vertical line. Benefits of fuse, they're quick, man. Look how slim your average trip region in is. They're real quick. I was walking my dog several years ago in the morning, and a fuse blew on the overhead distribution line. It sounded like a gunshot. And I called it in. I let them know, hey, you guys are missing some cutout fuses. Every time I walk my dog, I look up at the cutouts, and they're still just dangling open. All right, last one, and we'll wrap it up here because we're going to be approaching the end of this hour-long webinar. So here's our protection relay. What's ANSI 50 and 51 stand for? What's ANSI 50 and 51 stand for? Yeah, Daniel said the fuses are adjustable at its placeholder and at the on and blown position. Stands for overcurrent, sure. One of these is instantaneous. ANSI 50 is an instantaneous relay function. ANSI 51 is overcurrent. Back in the day, when we had electromechanical relays, like the electromechanical differential relay sitting on my desk behind there, we had to use these together in tandem, and we could wire their trip signals in parallel so that either the instantaneous could trip the breaker or the overcurrent could trip it. Nowadays, our relays, I've got I think that's also a differential up there on that bookshelf. That's a modern one, right? Microprocessor based. Nowadays, it's pretty much a computer, and we're telling the computer when to trip. So instead of having multiple relays for a combined function, now we have, one relay that can do it all. But how do we know this is a relay? A relay. The dead giveaway is I only have one line. I don't have a region. So a relay by itself sends a trip signal, but it's the breaker that opens. So when I've got a region, like a trip region, either in a fuse here, or my electronic trip breaker, or my thermal mag breaker, that's the average time that it takes that device to physically open and clear the fault and disconnect it. Well, all the relay does, the relay just tells the breaker when to trip. Relay sits there monitoring its input signals, typically from a current transformer for current tripping for overcurrent. And then it says, hey, boom, there's a fault, there's an overcurrent condition, there's an abnormal condition, your turn. It's like tag, you're it. And then the breaker is going to operate. But so here we have a 5051 protection relay. This would be our instantaneous trip. And this would be our ANSI 50 overcurrent, time delay, time overcurrent trip. And these are adjustable. Typically, we're plugging with an Ethernet cable or some proprietary communication protocol, and we're setting and changing these curves based on how adjustable the relay is. And some of them you can even program them just from the face of them. All right, any questions on this? We're right at 1 hour. So any questions? This will be our last one. Next week, we will pick up with applications. Any questions on this last example we went over? Anyone learn anything new? What was your favorite problem? What was your favorite problem we covered? You're welcome, Charles. Amen. You're welcome. Surge impedance loading. Yeah, that's easily the hardest one. Not every qualitative question on the P exam is going to be a real tough one like that. You're going to have a few. And if you've ever worked through one of my practice exams before, you know that I make the solutions as detailed as possible because we can ask you all day, what's the definition of surge impedance loading, or what happens when we terminate a transmission line with its surge impedance loading? But then what happens when it's greater than the surge impedance loading? What happens when it's less than the surge impedance loading? Why do those conditions exist? Where do they come from? What's the Ferranti effect? What effect does it have on the receiving voltage? So it's really helpful anytime you're working qualitative questions. Don't just think about the particular answer to that question. Always think about how else could they ask me this? What's the other related information to this problem that I could see on the P exam? What's useful to know in the context of this subject, right? They're not really asking you a problem. They're really testing you on a topic or a condition. So it's helpful to know a little bit more, right? We want to expand the scope of what we know about that condition. So it doesn't matter what particular question about it they ask us. Hey, we're ready. All right, everybody. That's about it for today. Again, the YouTube recording will be posted here probably in a couple of hours. I'll send out an email if anyone would like to watch it, and I will see you next week for week number 3, and then the week after for week number 4. Go ahead, get you a copy while it's still on sale at cost. You can get it for just 20 bucks. I think it's the best practice exam I've ever made. It's phenomenal for the power exam, and there's nothing out there like this right now, right? The exam is becoming more and more and more qualitative. You got to study these qualitative relationships. There is no other qualitative set of problems. So definitely want to include it in your study material to pass the PE exam. All right, everyone. Thank you so much for joining. Hey, see you next week. Bye-bye.